with minks, as I mentioned, we don't have specifically, we don't have imaging, but we have X-rays. And from those X-rays, we can see how much X-rays are being output during a solar flare. So here on this plot, I'm showing here the X-ray from minks, this huge increase. And the purple lines are from the GOES satellite that also measures X-rays, but doesn't give us spectral information. It just tells us about the channels, the X-ray channels increase and decrease. But with minks, which are the white squares, you can tell a lot of more. So this is what we get for our spectra, and you can see how it changes as we increase energy. And I want to point out around 2 kV, then we have a silicon line or a silicon future that we can see that it changes with time. So with our spectra fit, we can derive temperature, emission measure, which I'm not showing, but here's the temperature. We have a temperature that increases around 10 megakelvin during the peak of a flare. In the abundance over here, we can see that instead of being in the corona, which is when before the flare happens, the corona, we have a coronal abundance, but during the flare, it depletes to photospheric values, to the surface values. So we have this interesting combination of composition of the flare. And this can help us better understand how is the temperature or heating of the flare happening. So this was for M1 flare. So an M1 flare is a middle-sized flare. Showing here the AIA images, you can see the slopes being a little bit brightening all across. It's better in these hotter channels in the 131, which is probing around 10 megakelvin. And I want you to see that there's kind of this filament coming across, which we'll talk a little bit more. We also saw with XRT, which is X-ray telescope around Hinode. Again, these are X-ray images from the sun, and we can see the flare really bright here on the loops. So we can combine AIA and XRT to create some temperature maps. And these temperature maps have, we assume some composition. But with minks, we can assume what composition we can put in here. So in the temperature maps, we can see that during the pre-flare, it's kind of like a one temperature, but then right at the peak of a flare, we start seeing this plasma cloud that we had not seen in the images. But when we combine them, we can see this kind of heating that is happening on top of these loops. So that was quite interesting that we did not expect that there was this extra heating plasma cloud that we couldn't quite tell too much in the images, but we had seen it that the composition had changed, and that could have driven part of why this temperature map was different. So here's kind of a combination of images. It's kind of hard to tell, but if you put in kind of the brackets, you can see this filament kind of breaking into it and heating this plasma cloud that we can tell. So again, this is a data visualization and how we can combine data. So we have EUV images, X-ray images, and X-ray spectra. So kind of combining all of this, we can use thermal diagnostics to better understand the physics of what is driven through the flares. So here are the satellites, SZO, XRT, and minks. And I will publish what the temperature of a solar flare is, but I just want to say that it's actually all of them. So the temperature of flares, it varies. You can see it in all wavelengths. So it's not just a 20 megakelvin or a 5 megakelvin. It actually has all temperatures encompassed in it. And I want to acknowledge some people, Cheyenne Shi and Christopher Esmore, for always supporting me, the Minks and Hinode XRT, and especially the AU Freilich visualization competition for giving me the opportunity to speak. It was an amazing opportunity to be here, and I hope you had some fun with solar flares. Thank you.